Good afternoon, and today I'll discuss about some sample problems on week 11, which is about GML, and then I'll also solve some coding solutions like how to print coefficients and things like that. So I'll just wait 2-3 minutes before starting. So am I audible now? Okay. Okay. So today I will discuss about GMMs, and at first we will discuss about some sample problems, and then we will discuss about some coding solutions. So let's go through the first question. What does soft clustering mean in GMM? So we have four options, and we have to find out which among them are correct. Number one is that there may be samples that are outside any cluster boundary. So those samples are soft clustering. That is what the first option means. Second option is that uh, the updates during the maximum likelihood are taken in small steps to guarantee convergence, and uh, so the second option is that the updates during maximum likelihood are taken, and that is what we call as
Audio is not there.
is it audible?
Yes, now it's audible.
Am I audible?
Yes, now you're audible.
Okay.
Yes,
Okay. Thank you.
you're audible.
Okay. Thank you. So we have four options. The first question is that what does soft clustering mean in GMMs, and we have four options. First option is that there are some samples that are outside in a cluster boundary, and those samples we call as soft clustering. And second option is that the updates during maximum likelihood are taken in small steps, and these, if we take small steps, then it will guarantee convergence, and that method is called soft clustering. Third option is that it restricts the underlying distribution to be Gaussian, and because we are using only Gaussian distribution, so that is why we are calling it soft clustering. And a fourth option is that samples are assigned probabilities instead of 0 1, like to for a belonging to any cluster or another, and that one we called as soft clustering. So which option is correct? You can ask, like write in.
Option D.
Okay. Any more answers? Option A, I got option A. Okay. Any more answers? Let me go to the question.
No audio.
Yeah, I am not speaking right now. So I am waiting for more answers if anyone wants to provide. Okay, so let me continue. So we got two answers from the chat, and first one of the answer is that there may be samples that are outside of any cluster boundary. So here that is true. Like in JMM, this is possible, but they are not really called subclustering. So like that is not the point of JMMs. So in JMMs, what happens is that suppose you have two clusters and they might be say uh, like if you consider Gaussian distribution, what happens is that it is centered around the mean, right? So but in JMMs, what we want is that we want that a single point can belong to multiple clusters. So maybe with 0.6 probability, this is belonging to cluster 1. With 0.4 probability, it will belong to cluster 2. So that is because it is not, it is kind of like a softmax, right? So it is like with some probability, we are assigning something. So here, because the points in the clusters are not getting assigned to a single cluster, but probability, we are getting a probability that it will belong with this probability to this cluster, that probability to that cluster. So that is why we are called like this is as a soft clustering. Similarly, hard clustering is the same, like in KNNs, uh, is a single point can only belong to one cluster, right? So that is like hard clustering. Okay. So the correct answer is option D. Okay. So let me move on to the next question. Okay. So basically, you have four graphs, four plots, and this contains log likelihood function, and you have the initial values. So initial value is this here, this one, this one, this one, and this one. These four are the initial values, and the question is that which of them, which of the four options will reach the global maximum. So let's go step by step, like option by option. So option A. So do you think this will go to the global maximum? Will you be able to reach?
No,
Okay. Can you explain why?
because there is no local minimum. Only one minimum is there. No minimum actually is there.
Sorry, no minimum.
Only the last point is the minimum point. Or the first point is the minimum.
Here, here.
No optimum local minimum point.
Okay. So we want to actually reach maximum here. So is it possible?
No.
Yeah. So basically, currently we are at here, okay, and we are trying to go to this point, okay. So what will happen is that we'll like climb the hill. At this point, uh, on the left we have the like downward path. On the right also you have a downward path. So at this point, when we reach here, we'll not go there or there, so we'll get stuck at here, right? So this is actually not global maxima, this is global maxima, this is local maxima. So we'll get stuck at local maxima, and that is why like we cannot reach the global maxima if we start at this point. Okay. Okay. So let's go to the
Can you explain again? Please?
okay. So at the starting point we are here, okay, at this point, right? So we want to go to the maximum, so we are going to this path, okay, we are going here, this is local maximum, and from this point we don't have any further point,
So,
right?
voice is breaking, sir. Voice is breaking.
Okay, just wait a second.
Audio is not there. Audio is not.
Okay,
Sir, voice is breaking, sir.
just wait a
Not
second. Okay, okay.
Please repeat. No audio. No audio. No audio. No audio.
Okay, so am I clearly audible now?
Yes.
now it is okay.
Okay, okay. So let's go to the first option. So basically, we are currently we are here and we want to reach here, right? This is the global maximum. So what we'll try to do is that we'll try to go uphill. So here, from here we will go here, here like this. We will reach here. This is the local maximum. And from here, if we go left, there is like downward. This is like downward path. And also if we go right, this is like going down, right? So at this point, the maximum is here, right? So we will get stuck at this point, no, and we will not be able to reach here. So basically, this is global maximum and this is local maximum, and if we start at this point, then we'll get stuck at here instead of going here. So that is why we'll not be able to reach the global maximum, because there is some here it is like a downward path. There is a like from here we cannot reach here because because at this point we don't know there exists an global maximum, right? At this point, so we'll consider that if we go left, the value will decrease. If we go right, the value will decrease. So let's stay at here, right? So that is why like it will not be able to reach this point. I hope it is clear now. So
Yes, sir. Yes.
okay, okay. So in the second option, is it possible? First question, and is it like can you guarantee? Second option, second question. Is it possible to reach global maximum from this point, and is it guaranteed? So is it possible to reach here global maximum from option 2?
Yes, sir.
Yes, sir.
Okay, and is it guaranteed? Can you guarantee that it will reach the global maximum?
Because if we go right hand side, then it will reach the global maximum point.
Okay.
Uh, then there is no global maximum point in there.
Okay, so at this point we are at a minimum point, right? And from here we have two options. We can go either right, we can go either left, right? So basically there is no guarantee that we will choose the right path. If we go to the right path, we will reach the global maximum, but if we choose the left path, we will reach here and we will get stuck here. Okay, so yeah, it is possible that it is it will like we will be able to reach this, but this is not guaranteed. Like from here we have two choices, left and right. If we choose left, then we will not be able to reach here. Okay, so this is not really a correct option, because this is like we cannot really guarantee that we will reach here. Okay, because you have two options here and only one of them are going to the global maximum. So option 3, we are starting here and we want to reach here. Okay, so is it possible and is it guaranteed?
Yes, it is guaranteed.
Yep. Yeah. So basically you can see here we are going through this, so uphill, then also this is like the slope is uphill, will go again again. So everything here is uphill, there is no downhill slope, right? So we'll be able to reach at this point. On this point, on left there is downward, on right there is downhill. So we'll stay here, but this one is the global maxima. So yes, we can guarantee that we can reach this point. Okay, and last one.
It is also correct.
Okay,
If you go left side,
are you sure?
because in the right hand side nothing is there.
Okay, but if you go to the left, if you come at this point, this one is downward, right?
Okay,
Yes,
very small.
very small, but it is downward. So basically you will come at this point and you will get stuck here. Okay, so even in this case you will not be able to reach the global maximum. So only the correct option is that option C. Okay, so I hope it is clear to all of you. Option C is the correct answer.
Sir, can you explain once again?
Which one? All of them?
Yes, sir, all options.
Okay, okay. So at first we are starting here and we want to reach the global maximum, which is here, right? So if we go to the right, we'll come here, but from this point, this is like downward, right? But in this, what we do is that we always go upwards. Okay, we always try to go upward. So when we come to this point, uh, on the left we have a downward slope. On the right we have also downward slope. There is no upward like position here, upward point from here immediate. So at this point we'll get stuck and uh, we'll not be able to reach here. So that is why this is not a correct option, because we'll not be able to reach here. We'll remain here. Similarly here, if we go to the right, this is like uphill, so we can reach here. But if we go to the left, there is this point and we'll get stuck here. So basically, this is the minimum, and from this point we can go either left side or the right side. But here, there is a definite slope and we can go only this side, only right side. But here, this is the minimum and we can take either side, left or right. If we go to the right, we'll able to reach here. But if we go to the left, we'll able to reach here. And if we reach here, this is not the global maximum. So yeah, it is possible that we will be able to reach here, but it is not guaranteed, because at this point we can either go left or we can go right. So it is not guaranteed that we will reach here. Okay, here we are starting from here, and this is like uphill slope, and from here again this is like uphill, and here also like till this point. So if you start from here and go to this point, everything in the path is like uphill, right? There is no downward point, so we can reach this here, global maximum. Okay, but if you consider here, we are starting from here, we are reaching here, but here we have a downward point. So from this point we will consider that if we go left, there is a downward point. If you go to the right, there is downward. So we'll get stuck here instead of reaching here. So that is why this is the global maxima, right? So here it is local maxima. So we'll get stuck at here, and that is why this is also is not a correct option. So only correct option is option C. So this is a GMM model, and you have to find out what is the value of K.
Sir, it is not moving, sir. Now it is
Okay.
little bit late, I think, lagging.
Okay.
Your cursor moving also very lagging.
Okay, fine. So yeah, is it visible now?
Yes,
Yeah. So like we have a GMM model, and we have to find the value of K. Like from this diagram, can you find what can be the value of K here? How many clusters are there? Sorry, I just saw the answer. Anyway, So okay, so basically the correct answer is 4. Okay, and how to find the clusters? So at first you can see this one is one cluster. Okay, and this one is another cluster, this one is another cluster, and this one is another cluster, right? So you can, if you consider the Gaussian, right, so you can see
So
the
cluster is sorry, cursor is not moving.
okay, anyway, so uh cursor is not moving. Is it visible now? Okay, just consider this. This is a like around 0, like above 0. On the x-axis we have the first cluster, and around above 5 we have the second cluster, and around 10 we have the two clusters, right? So uh, this is like total 4 clusters. So you can identify them by like, if you consider how many circles are there. So on the left we have one circle, and on the right we have 3 circles, and like if you consider Gaussian distribution, you can consider that in the middle, around the middle of each of the circle we have the a dense points, like the most number of points around the middle, right? So total 4 clusters are there in the like JVM model, because if you consider the points, you can see there are 4 circles. Okay, so
So which one the four circles? Four circle I didn't understand.
so
Can you draw it the circle one circle so it will be clear?
okay, so my like cursor is visible now?
Cursor is visible, but it is moving very slow.
Okay, fine. Okay, so let's just show from here. Okay, so this is the one cluster. So I hope my mouse is right now visible. I have pointed it right inside a cluster. Okay, so this is one. Okay, and if you go to here, okay, so this is another one. So just this point, this circle, small circle. So even though, like, complete circle is not visible, because this is like at the same point there are 3 clusters, but if you consider here, uh, this is one of the cluster, then here this point, this is another cluster, and this one, finally the lower one, this one is also another cluster. So if you draw the circles here, you can like find out. This is kind of like this, this is like this, and this is like this. So okay.
So, but in the left hand side circle, you are asking that it is three circle, but it is uh, all are connected. No, sir, three circles.
Yes, all are connected. So that is basically what we do in GMMs, right? Because we can consider these points on the right side as like a mixture of multiple these points. They belong to this cluster also with some probability, right?
Multiple cluster,
Yes,
soft clustering.
yes, yes.
It is possible only in GMM.
Yeah. So basically, if you can
And
actually.
sir, what is the outer line? Outer line denotes the outer
Okay,
lines.
so like these are called contours. So they basically within. So basically, if you can see, they are kind of let's say of similar shape of that of the clusters, right? So within like certain distance, they are belonging to those that kind of thing, like within certain ranges. So suppose.
Okay.
Okay, suppose in the previous question we have seen that we have four clusters, but suppose we don't want four clusters. Suppose we want a number different than four, but we want similar kind of clustering. So, what could be the number to achieve that? 3, 5, 6, 7. How many clusters do we need to like get a similar, like get this figure? But here we have four clusters, but we are saying that we'll only need either 3 or 5 or 6 or 7, but not 4. Okay, I got one answer. And then,
Show the questions.
yeah, I got one answer, and anyone would like to answer? We have four clusters, and we want a minimum value, and so that we will get very similar cluster, but k should not be equal to 4. So the correct option is 3. So basically, uh, you can see the on the right side, these and these two clusters are very close, and if we merge them, then also the clusters will be really similar, right? Because this will be one cluster, the left one. On the right one, the middle one will be another cluster, and on the extreme right side, we can just merge these two clusters. So like 3, we want the minimum. So 3, with 3 also we can get a very similar cluster. So 3 is the correct option. So like why we are considering this and this and not this and this? This is actually, you can see, like very close compared to this and this. So that is why, like if we merge these two, we can still get very similar assignments. So this is the final question uh, with this diagram. So basically, uh, at first, when we are considering that we have four clusters, we consider that we have uniform. Okay, so like I assume equal pi I. So basically, what they are saying is that when we consider that k equal to 4, we had equal pi I for every like case. Okay, like pi of 1 also is same, pi of 2 also is same. Okay, and after merging, we are what is the pi I is will get. So initially, can you say what was the pi i's with, like when k equal to 4, if we consider equal pi I, what is the values of the pi i's for all the case? So summation of all the pi I is what? If you suppose k equal to 4 and we have pi 1, pi 2, pi 3, pi 4, and if we sum all of them, what would be the value? So basically here equal pi I means we are considering that each of the clusters have equal number of points. So basically the sum of pi I for is equal to 1. Okay, because this is the all the points. Okay, all probability of belonging to all the clusters. So if we just sum this summation of I over pi of I, okay, equal to 1. So we are assuming that they are equal, and we have 4k, right? So what are the initial values? Initial values will be so total 1 and we have 4. So what will be the values? All of them are equal. 0.25, 0.25, 0.25, right? 1 divided by 4, and that is 0.25, right? So this is the initial value, and we are merging two of them. So what will be the value now when k equal to 3?
Point two five, 0.25, 0.5.
Right. So basically here we are not merging it, so it will again remain, the number of points here will remain the same, 0.25. Here also we are not changing it, it will remain same, 0.25. Since we are merging this and these clusters, they are becoming a single cluster with combined all the points, right? So that is becoming the sum of all those 0.25 and 0.25, which is 0.5, right? So this is the correct option. Okay, so next question. Suppose we are trying to model a p-dimensional Gaussian distribution. What is the actual number of independent parameters that needs to be estimated? So this might take a little bit time, so you can find out. I'll give you some time. Okay, so let's go to the solution. So the correct option is that p into p plus 3 divided by 2. And how we are getting it? So basically, to estimate the number of parameters, so to find the number of independent parameters, at first we need to find the mean vector. So for the mean vector, so suppose it is like p-dimensional Gaussian distribution. To find the mean vector, we will have to find there are p parameters, okay, one for each dimension. So p-dimensional Gaussian distribution, for each dimension you have to find out the mean. So there are like p number of calculations, like p number of parameters there, okay. And then covariance matrix. So covariance matrix you can find by how many like covariance matrix contains how many unique values, I mean independent values, how many independent values. So okay, let's just show something. Just wait a second. Okay. So suppose we have let's say 4 dimensions, okay, and we have to find covariance matrix. So let's say here dimension 1, dimension 2, like this. So covariance matrix, what happens is that we have to, this is like covariance matrix is symmetric matrix, right? So suppose it is like one, say anything like so in covariance matrix what will happen is that it is symmetric. So if we are calculating this, we don't need to calculate this because they are equal, right? So basically what we can do, we can just calculate the one side, like diagonal, this part, let's say right. So if we know this, we can push it here, right? If we know this, we can just copy it here. If we know this, we can copy it here, like this, because this is like symmetric matrix. So how many values do you need to calculate here? So if you consider here the values, number of like items we need to calculate is n into n plus 1 divided by 2. So here n equal to 4, so 4 into 5 divided by 2 is 10, right? So 1 2 3 4 5 6 7 8 9 10. So for this matrix we need 10, we need n into n plus 1 divided by 2 number of parameters, and for the mean vector we need uh, n number of parameters. Okay, so if we add them, then so p is for mean vector and p into p plus 1 divided by 2 is for the covariance matrix. So if we add them, so 2 is in the denominator, so if we just multiply that, 2p plus p into p plus 1 and everything divided by 2, right here. Then if we take the p common here from both the sides, so p common 2 plus p plus 1, so p plus 3 divided by 2. So this is the correct option. So let me just write it here. We are taking p common, so 2 plus p plus 1 divided by 2 equal to this. Okay. Okay, so we have a Gaussian mixture model and pi I are the mixing coefficients. So we have 4 options, and we have you have to find out which among them are correct. There might be multiple correct options. So any answer on this? Okay, so I got B, and BC. Okay. So correct options are both B and C, because pi I is the mixing coefficient, so that is like how many like probability of belonging to the clusters, right? So like so basically this is correct because that probability cannot be less than 0, so maximum 1, minimum 0. And also, like in the previous, also like in this question, I was telling, right, so a summation of all pi I equal to 1. So there are, suppose 4 k equal to 4, then if we sum all of them, pi I, pi 1, pi 2, pi 3, pi 4, they will be equal to 1. So both B and C are the correct options, not only B. Okay, so we have a set of points here.
Can you show the answer?
Yeah, B and C.
So what is that symbol? The reverse is, what is that called?
Which one?
Second
Okay.
option, the last
Okay.
donation.
Yeah, this is for all eyes.
Oh, for all eyes.
Yeah. So if you
What is the symbol? What is the symbol called?
yeah, you can see this is called actually for all.
For all.
So if you consider all the i's, then like pi I will be for all the i's, pi I will be less than 1, less than equal to 1, and greater than equal to 0. So that is what we say.
Okay.
So this is the final question. So final diagram actually. So basically we have a diagram here, and these are the points, and from GMM with k equal to 2 we got this cluster 1 and cluster 2. So is there any problem with this kind of clustering? So this is one cluster, this like you know the inner blue circles, and those are the clusters assigned. So is there any problem with this kind of clustering, or is it correct? If there is a problem, what are the problems? Option is that pi 1 are too big. Okay, so pi 1 means like probability of belonging to a cluster, so that is too big. Then clusters are not sampled from a Gaussian distribution, and option third is GMM has not been converged yet. So if we train it for longer, then it will be able to learn better. And option 4 is that there is no problem, this is like absolutely fine, this kind of clustering. So in Gaussian distribution, what do we consider? That it has the most points near the mean, right? So if we consider this as the cluster, around this we should have the mean, but here we have no points. Similarly here around center we do not have any points. So that is actually not really a, you can say, Gaussian, right? So near the mean it should be there should have the maximum number of points, because this is kind of like this kind of distribution. Near the mean we have the highest number of points. So the correct option is that. So basically GMM has not converged yet. This option is not correct, because even if we train for longer, maybe the circles will go bigger or go to different point. But again, no matter how you try to fit it, the two circles, you will not get the most number of points near the center. You will not get kind of like Gaussian kind of distribution. So this option is not correct, and pi i's are too big, that is also not correct. That is not really a problem here, even if they are big, right? So the only option is that the clusters that we are sampling using here, they are not really following the data set itself. Even if we try to fit the cluster here, any way you try to fit it, because the data is not from Gaussian distribution, we cannot really do it with k equal to 2, right? So this is the correct option, that clusters are not sampled from a Gaussian distribution. Okay, so what is the solution of this problem? So how can we improve that? How can we have the most of the points near means of the clusters, near the center of the clusters? Can we increase k? Will that help? If we initialize it differently, will it help? And maybe if we can train it for much longer iterations, will that help? Or is it not possible with GMMs? So the correct option is that increase k. So basically what will happen if we use a better initialization, suppose we are initializing here or anywhere, it will not matter, because this distribution itself is not Gaussian. So no matter where we start, it will not help, because if we draw the circle here or here, no matter where, most of the points will never be near to the center of the cluster. Then if we learn from more iteration also, this will not help. But if we increase k, then maybe we can have a let's say, okay, let me draw this. Okay, so we have some points like this, and some points like this. Okay, with 2 we cannot do anything, but suppose we have let's say 10, k equal to 10, so you can draw 1k like here, right? This is 1k, so this is near the center we have all the points, right? And then another k we have here, another k we have here, like this. So near the center all the points are there. Similarly for here, if we increase the number of k, this is possible, right? So yeah, even with let's say 8 or 10 or if we increase k, we can feed those clusters in this way, and though most of the points will be near the center here. So here suppose instead of here we can draw it here like this, here like this, and it will work. It will be much better. The most of the points will be center of the individual circles. So this is how, if you increase k, then this will work. This will be much better. Okay, so these are the questions that we are supposed to discuss today. Then I will go to the coding. So we'll discuss 3 things. At first we'll try to find out mixing coefficient, and then find log likelihood, and then find okay, I'll come here. Okay, so let's focus on the mixing coefficient. So I'll go to the Colab. Okay, so at first, how to use GMM scikit-learn. Let's check out the documentation. Okay, so let's at first import the libraries, and we have to also import this, right? From sklearn.mixture import. Okay, So this we have imported, and let's define some data. Let's define some 2D data maybe. Okay, so np.array. For 2D we need to 1 comma 2, suppose this is 1 point, 2 comma 3, 2 comma 2, 4 comma 5, and 3 comma 6. Suppose these are the points. Okay, so 5 points. Okay, so then we have to find out we have to let's initialize a Gaussian model. So this is what we have imported from here, right? And let's say we have to give number of components, so basically k in components equal to suppose 2, and random state maybe 42. Okay, so let's run this. Okay, there is some spelling mistake. Okay, yeah. So we have initialized the GMM model, and then we have to feed the data to the GMM model. So gmm.feed data. Okay, so it has been trained. So now we have to find the coefficient. How to find it? Okay, so these are the values that the model will provide. Okay, so weights are the weights of the mixture component. Okay, so if we got the we have initialized the GMM here, we have fitted the data, and after fitting what are, if we go to the this value weights underscore, then we'll get the coefficient. Okay, so GBM dot weights underscore, and then print okay. So coefficient is 0.4 and 0.6. So this is how you find out the coefficient of the GMM. Then let's go to the next question. So suppose you are given some new points, and you have to find out the log likelihood of those points. Okay, so log likelihood given new points. So let's say new points is the another data np.array, and maybe 0, 1, 2, 4, and 1, 3. Suppose these are the new points. Okay, so we want to find log likelihood of these points. So how to find this? So okay, so there are two methods. One is score, another one is score samples. So if you use code, you only give only one data point. If you use score samples, you can give multiple data points. We have 3 data points here, right? So we will use score samples and it will return log probability. Okay, so log likelihood equal to gmm dot score samples, and here we will give the new points, right? Then let's print the log likelihood. Okay, so these are the log likelihoods of the 3 points here. Okay, so if you are asked to choose the minimum one, you have to choose this one. If you are choosing the maximum one, you have to choose this one, right? So this is how you find the log likelihood. Okay, so then finally, suppose you have two models, okay, and two models in the sense you have two GMMs, and you have to find out that if the labels are getting different between two models. So suppose what you mean to say is that suppose here let's say I have taken GMM equal to Gaussian mixture and component equal to 2, random state equal to 42. Okay, so instead of that, suppose we are doing it differently, maybe GMMB, and n components is suppose 3 and random state is suppose maybe 50. Okay, so we have a model A there, GMM, and model B is GMMB, right? So it is initialized. We have to fit it again the data. Okay, so data has been fitted, and if we want to find the coefficient, so what's underscore. Okay, so here also we are getting 0.4 and 0.6. Okay, just a minute. Yeah, okay, maybe let's add some more points. Okay, here maybe 8,9, 9,9, 9,10. So uh, so basically we have two models right now, okay, model A and model B, and we have to find out that if we predict from model A, then how many of them are correct coming to the same cluster, but if we are using model B, how many of them are getting different. Okay, so let's define from the scratch. Okay, so model A equal to okay, and we have to also get the labels right after prediction. So we'll use output model A equal to model A dot fit predict. So it will first fit the model and then it will predict on the same data. So that is we have data. Okay. Similarly for model B, we'll repeat model B in components equal to 3 and model B. Alright, so let's increase the dataset further for better thing. Okay, so it will be better if we use larger dataset. We will be able to separate the distance, like understand it, like if we use larger number of value data, then maybe larger number of points will get separated in one model from the another. Okay, so we have two models, one with n components equal to 2, another with n components equal to 3. So let's run this and find the outputs. Okay, print output okay, so this is the output of model A and this is the output of model B. Okay, so what is happening is that model A is assigning last two values, last two data points into one cluster and rest of the data points in another cluster. But model B is providing last two values into one cluster and these values into another cluster and these values into another cluster. So if you consider that which of the points were having same level first but are different now. So if you consider these two, 1 1, so they were same before, and here 2 2, they are same level now. Okay, and 0 1 they are different, 0 2 they are different, so this is fine. But if you consider here 0 0 and here it is 1 0, so there they were similar and there they are different, right? So our task is that then finding the number of points that are like this. Okay, so how can we do this? Let's run a for loop for I in range len of so we'll iterate through all the values here, then we'll start comparing from the previous one, right? Like the next one, for j in range I plus 1 to len of so basically what we'll do is that we'll go through all the points here and compare with itself, and if they are similar, then we'll check that if they are similar in output model B2. Okay, so at first we are going through I here, this point, then we are coming here J, so we'll check that if they are similar. Okay, so if output model A I equal to basically we are checking if they are similar. So if they are similar, then only we will check that if output of model B are also similar. So if output model B of I is not equal to then only we'll print that point and were similar because like we are using index, so that is why I have written I plus 1 j plus 1. So way too many points are having this kind of properties. Okay, so 1 and 5, first point and fifth point, yeah, so they were same in model A, but they are different in model B. Okay, 4 comma 9, so fourth is this one and ninth is this one, so they are also having similar points earlier, like similar levels earlier, but now they are having different levels, right? So this is also another. So if you want to count how many of them are there, so you can also do that. Count equal to 0 and okay, so total 20 such pairs are there where it was different, it was similar earlier, but it is different now. Okay, so if we consider the reverse, like how many of them are same in this one but were different earlier? So can you, from these levels, can you tell how many of them such are there, like similar in this but different in here? So actually the number is 0 because these two are similar here, they are also similar here. If you just take any two points, and if they are similar, they are actually also similar here. Maybe like 1 1, they are similar here, and they are similar here also 0 0. So both are equal. Here also 1 1, here also 0 0. Both are same. So if you just consider this, it should be 0. So let's find out with program. So instead of output model A, so output length is fine because both of the lengths are both of the lengths of model A and model B are exactly same. So we don't need to modify that. Only we need to modify here, right? So basically we are checking if the outputs are same in model A, model B, then only we are checking if they are also same in model B. If not, then we are facing some issue. So it should be equal to 0. Yes, the total is 0. So this is how you use GMMs. So if you have any doubts regarding this, you can ask me. Okay, so let's just run everything again from scratch. Okay, so initially it was 20, now it is 12. How is it happening? Because we haven't mentioned any random state, so every time it is getting initialized randomly, so that is how it is changing. So if we assign random value, then it will provide same results every time. So every time it should be 20 right now. Yes. So if you don't have any doubts, then I will end the session. And yeah, I'll share the code along with the slides.
Sir, have you given the same data for both the models?
Yes, same data. So basically we are showing the data here and here. Let's say Gaussian mixture n components. So when you are fitting it, fit predict, we are providing the data. Here also we are providing the data, the same data. So only difference is that we have the two clusters here and k equal to 3 here. So you can see here also only two labels are here and three labels here, unique labels.
Okay, sir.
So yeah, I'll upload the code as well as the slides in the spreadsheet. Okay. So thank you everyone for joining.
Sir, what are the things we have to change in the code for solving the assignment?
Not much, but that you have to figure out. So at first, I guess you have to change the data, you have to change the number of components. I guess that is same, and you have to also change the random state.
Okay.
Okay then. So thank you everyone for joining, and have a nice day. Goodbye.
Just share your coding in the Google Drive.
Yeah. So actually, you have access to the Google spreadsheet, right? Where we upload everything.
Yes, yes,
Yeah, I
yes.
will upload it there.
Okay.
Yeah. Thank you.